The night sky is lying to you. What looks like a universe overflowing with stars is actually the emptiest place we've ever measured, and it's getting emptier while you watch this. In 1995, Hubble pointed at a patch of nothing and found 3,000 galaxies hiding inside it. That should be reassuring. It isn't, because everything you can see, every star, every galaxy, adds up to less than 5% of what's actually out there. The rest is invisible, something called dark matter holding galaxies together, and something called dark energy tearing them apart faster every second, with no sign of stopping. Tonight, we explore why the cosmos is mostly empty and uncover the terrifying reason behind it. Now get yourself comfortable, hit subscribe, we begin. Step outside on a clear night, far enough from the city that the sky opens fully, and look up. Give your eyes a few minutes to adjust. Let the stars emerge from the dark one by one, and somewhere in that process, almost inevitably, you will feel something ancient stir, a quiet, wordless sense that the universe is a full place, thick with stars, generous with light, ancient and alive in every direction you can turn. That feeling is one of the most profound deceptions ever visited upon the human mind. The universe is not full. The universe is nearly incomprehensibly, terrifyingly empty, and the sky above you is not showing you reality. Step by careful step, we are going to dismantle the illusion, and what waits on the other side is stranger, quieter, and more unsettling than the starlight has ever suggested. On the finest possible night, in the darkest possible location on Earth, the unaided human eye can resolve somewhere between 2,000 and 5,000 individual stars. The exact count depends on your vision, your sky conditions, and how long you let your eyes adjust to the dark. But that is your ceiling, a few thousand points of light scattered across a dome of darkness, and standing beneath them, the sky genuinely feels like it means something. Dense, ancient, full. Here is what that number actually represents. Every single one of those stars lives within our immediate cosmic neighborhood, our local corner of just one galaxy, the Milky Way, which stretches roughly 100,000 light-years from edge to edge. 1 light-year is the distance light covers in a full year, traveling at approximately 300,000 kilometers, about 186,000 miles, per second. Right now, the glow of whatever screen you're watching on is crossing the room at that speed, bridging the distance between light source and your eyes in an unmeasurable instant. Light is the fastest thing in the known universe, and our galaxy spans 100,000 of those year-long journeys, edge to edge. The stars you can see on the finest night of your life, nearly all of them live within a few thousand light-years of where you stand. We are not seeing our galaxy, we are barely seeing our own street. 100,000 light-years of Milky Way stretches in every direction around us, and almost all of it is invisible to unaided human eyes. In December of 1995, an astronomer named Robert Williams was running the Space Telescope Science Institute, the organization that operates Hubble for NASA. He had an idea that most of his colleagues considered reckless. He wanted to point the most powerful space telescope ever built at a patch of sky near the handle of the Big Dipper that appeared, to every available instrument of the time, to contain essentially nothing. A small, quiet, dark window between the stars. A piece of sky you would never think twice about. His colleagues were direct. The committee would never approve it. Hubble's time was precious, and staring at blank nothing for this long, they warned, was a waste of something the entire scientific community wanted access to. Williams listened to every objection, and he did it anyway. As director, he had personal discretionary control over a portion of Hubble's observation time. Scientific discovery requires risk, he later said, and I was at a point in my career where I said, if it's that bad, I'll resign. I'll fall on my sword. Between December 18th and 28th, Hubble stared into that blank window for 100 consecutive hours, accumulating light one photon at a time. A photon is a single particle of light, the smallest possible unit of illumination. The telescope gathered them patiently, silently, from objects so faint and so distant that no instrument had ever collected enough of their signal to form even a coherent image. What came back left the scientific community speechless. Inside that apparently empty field, a patch of sky small enough to hide completely behind a pinhead held at arm's length, astronomers found approximately 3,000 galaxies. Not stars, galaxies, each one a complete island universe, each containing hundreds of billions of stars of its own, each sitting at distances measured not in years or centuries, but in billions of light years. And that was one patch of apparently empty sky. When astronomers later swept other blank windows, the Hubble Deep Field South in 1998, the Ultra Deep Field in 2004, and the Extreme Deep Field assembled from years of accumulated data, the same discovery appeared every time. Galaxies in every direction, hiding inside every piece of darkness the human eye had always dismissed as nothing. The sky had not been empty. The sky had been full of galaxies the entire time. But here is where the story cracks open. Because galaxies in every direction does not mean what it may initially seem. When you look at the night sky, you are experiencing the universe collapsed into two dimensions. Think of it like a photograph taken directly above a vast forest. Trees everywhere, overlapping, appearing dense and close-packed. But a photograph cannot show depth. Some trees might be 10 meters away, and others 10 kilometers. From directly above, they all look equally close. They all appear to fill the same space. The universe does this to us. All those galaxies, stacked behind each other across billions of light years in every direction, look crowded from our fixed point in space. The three-dimensional reality is something else entirely. The observable universe, the portion of space from which light has had enough time to reach us since the universe began, spans roughly 93 billion light-years from one side to the other. That may feel paradoxical, because the universe is only about 13.8 billion years old. How can something 13.8 billion years old span 93 billion light-years? The answer is that space itself has been expanding continuously since the beginning. Objects that emitted light billions of years ago were relatively close to us when they released it, but the space between us and them has been stretching ever since, carrying those objects far beyond the distance their ancient light originally crossed. The universe is not just old, it is continuously, relentlessly growing in every direction at once, which means distances are not fixed. They are increasing, even now, as you watch. Current estimates suggest somewhere between 1 trillion and 2 trillion galaxies reside within our observable reach. Those figures carry genuine scientific uncertainty. They depend on assumptions about early galaxy sizes and what instruments can detect at extreme distances. Scientists continue to debate the best estimate. What is not in debate is that the number is staggering, and yet every single one of those galaxies floats in separation so immense that the word vast stops feeling adequate somewhere along the way. Let's put this in perspective using something you can hold between two fingers. Shrink the Sun, a star 1,392,000 kilometers wide, roughly 865,000 miles across, down to the size of a single grain of sand, 1 millimeter, small enough to lose in the crease of your palm. At that exact same scale, the nearest star to our own, Proxima Centauri, sitting 4.24 light-years away, would be located approximately 29 kilometers, or about 18 miles from that grain. Not 29 meters, 29 kilometers, a half-hour drive on an open road. Imagine you were placed somewhere in that gap, suspended in the open space between those two grains, in what would be the most common environment in our galaxy. No warmth from either star would reach you, no sound, no light beyond two faint points in an otherwise absolute dark. Nothing your body could register as presence. The gap between our Sun and its nearest neighbour, scaled down by a factor of over 1 trillion, would still require an 18-mile drive to cross, and Proxima Centauri is our closest neighbour, the nearest grain in the cosmic beach. Scale further outward. The Milky Way, our 100,000 light-year galaxy, home to somewhere between 100 billion and 400 billion stars, sits separated from its nearest large companion, the Andromeda Galaxy, by approximately 2.5 million light-years. That gap is 25 times the full width of our own galaxy. Every star in both galaxies, and every light-year of space between them, belongs to what astronomers call the local group, a small family of galaxies that, despite the company, consists overwhelmingly of cold, unoccupied space. The separation between things is the real story, not the things themselves. Before we go further, something deserves precision. When scientists describe space as empty, they are not describing philosophical nothingness. Quantum fields thread through all of space, invisible structures woven into the fabric of space-time itself, present everywhere and impossible to remove. Faint particles drift through the interstellar medium. Ancient radiation crosses the dark in every direction. Magnetic fields lace through galaxies in long, invisible ribbons. And between galaxy clusters, in volumes once assumed completely bare, a diffuse, warm, hot intergalactic medium, an extraordinarily thin, extremely hot plasma, fills much of what appears at first glance to be nothing at all. In fact, most ordinary matter in the universe, the atoms making up every star, every planet, every living thing, does not reside in stars. Current measurements suggest the majority of ordinary matter resides in these diffuse intergalactic filaments, spread so thin across such enormous volumes that decades of astronomy passed before instruments could begin to detect it. Distribute all the ordinary matter in the observable universe evenly across its full volume, and the resulting average density amounts to roughly 1 hydrogen atom for every 4 cubic meters. Picture 4 large household refrigerators stacked together, and inside that entire space, just one solitary atom drifting alone. Not a molecule, not a particle you could weigh, one isolated atom in a space you could walk around. You may have encountered the claim that atoms themselves are mostly empty space, that electrons are so far from nuclei, the matter of everyday life is essentially hollow. But this dissolves under examination. Atoms are not miniature solar systems with literal gaps between solid parts. At quantum scales, the rules change entirely. Electrons do not trace fixed paths. They exist as probability distributions, quantum clouds, fields of potential and energy that defy any simple spatial picture. The emptiness inside an atom is not the same as the emptiness between stars. Calling them the same thing misrepresents what quantum mechanics actually describes: the genuine emptiness, the kind that defines the universe's deepest character, exists between atoms, between stars, and between entire galaxies. And at those scales, the scarcity of matter is not a metaphor. It is a measured fact. And here is where the question sharpens into something genuinely difficult to look at directly. The earliest universe, as best as we understand it, was nearly uniform, smooth, matter distributed with extraordinary evenness across expanding space. No stars, no galaxies, no dramatic concentrations, just an expanding fog of matter, cooling as it spread, nearly identical in temperature in every direction. Today, that matter is not smooth, not even close. Matter has collapsed into violent concentrations, stars, galaxies, superclusters, while the space between them has grown into abysses hundreds of millions of light-years wide. Something took a smooth beginning and fractured it into islands. Something built the void between them. Something made the universe empty, and the sky above us, beautiful, generous with ancient light, apparently crowded, hides all of it. The projection hides it. The local stars hide it. The very way our eyes evolved to navigate an environment the size of a continent hides it. What we have assembled here is not a list of impressive distances. It is a confrontation with the gap between what the sky appears to be and what the universe actually is. a gap far wider than any distance between stars. The stars visible to the naked eye are all local, the galaxies concealed inside. Every blank patch of sky are beyond direct counting. The space between all of them operates on a scale no instinct was ever designed to process. And all of this, every star, every galaxy, every atom in every intergalactic filament ever measured, accounts for roughly 5% of the universe's total content. 5%. The visible universe is a skin, a thin, luminous surface stretched over something far larger, far darker, and far stranger than the sky has ever suggested. 3 nested scales of emptiness surround every observer in the cosmos: the space between planets, the space between stars, and the space between entire galaxy systems, each one more complete, more absolute, and more unsettling than the last. The darkness between the stars is not the space between the important things. The darkness between the stars is most of what the universe actually is. The remaining 95% does not glow, does not emit radiation any instrument has yet directly detected, does not interact with light in any way our current technology can observe, and yet something within that darkness is controlling the structure of everything visible, pulling matter into specific patterns, shaping galaxies from the inside out, building the invisible scaffolding upon which all luminous things are suspended. The emptiness is not random. The void has an architecture, and something that occupies the space where no light falls has been the dominant force shaping this universe since long before the first star ever ignited. We cannot see it, we cannot touch it, but we can measure with extraordinary precision exactly what it does to everything around it, and what it does, quietly, invisibly, across every scale from individual galaxies to the largest structures ever mapped, was something no one predicted, something no one was even willing to believe was real, and something that ultimately forced an entirely new picture of what the universe is built from. The story of how we found it does not begin with a triumphant discovery. It begins with a man almost no one believed. In 1933, an astronomer named Fritz Zwicky was working at the Mount Wilson Observatory in California, studying a distant gathering of galaxies known as the Coma Cluster. The cluster sits roughly 320 million light-years away. Light travelling at approximately 300,000 kilometers, about 186,000 miles, per second took over 300 million years just to reach his telescope. Zwicky was not looking for anything revolutionary. He was simply trying to measure how fast the galaxies inside that cluster were moving, relative to one another. What he found made no sense. Using a mathematical tool borrowed from thermodynamics called the virial theorem, a method that relates how fast objects move within a bound system to how much mass must be holding that system together, Zwicky calculated the cluster's total mass from its galaxies' velocities. Then he calculated a second mass estimate, this time based on how much light those galaxies actually produced. 2 methods, 2 answers, and they did not agree. The mismatch was staggering. The galaxies were moving so fast that based on the gravity supplied by their visible light alone, the cluster should have been ripping itself apart. Zwicky's velocity-based estimate came out roughly 160 times greater than what the visible matter could account for. Imagine pulling on a rope and discovering it holds you in place with the strength of a steel cable, except every fibre you can see is thread. Something invisible inside the Coma cluster was supplying gravity that the light could not explain. Zwicky called it Dunkel Materie, dark matter. His colleagues were not impressed. The astronomical community of the 1930s had no framework for an unseen mass that did not glow, did not block light, and did not behave like the dust and gas already known to exist. Zwicky felt the rejection as something close to hostility. His proposal was filed away as an interesting anomaly and largely ignored for almost 40 years. But that is not the whole story. Nearly 4 decades later, in the late 1960s, an astronomer named Vera Rubin began a different kind of investigation, working alongside an instrument maker named Kent Ford. Ford had built an extraordinarily sensitive spectrograph, a device that splits starlight into its component wavelengths to measure how fast an object is moving toward or away from us. Rubin pointed it at the Andromeda Galaxy, our closest large galactic neighbour, sitting approximately 2.5 million light-years away. She wanted to measure something deceptively simple: how fast individual stars orbit the galaxy's centre, depending on their distance from it. Here is what she expected to find. In our own solar system, planets close to the Sun, like Mercury, orbit fast, while planets far away, like Neptune, orbit slowly. That happens because gravity weakens with distance, and most of the system's mass sits concentrated at the centre, in the Sun itself. Rubin expected galaxies to behave the same way. Stars near a galaxy's bright, dense centre should orbit quickly. Stars out near the faint edges, far from most of the visible mass, should orbit slowly. That is not what she found. The orbital speeds did not decline. They stayed almost level, all the way out past the visible edge of the galaxy's disk. Picture a carousel where the horses near the centre spin at the same speed as the horses near the rim, every single time on every galaxy she examined. Rubin recalled the moment plainly. I remember thinking that there must be some mechanism for speeding up stars that move too slowly, she said, or slowing down stars that move too fast. Neither mechanism existed. The data simply refused to match the visible mass. Rubin did not stop at one galaxy. Over the following decade, she and her collaborators measured rotation curves for more than 75 spiral galaxies. The same flat pattern appeared again and again. Stars at the outer edges, far beyond where the visible starlight thinned into darkness, were orbiting just as fast as stars near the core. According to the laws of gravity, those outer stars should have flown off into space entirely. They didn't. The only explanation that held together was the one Zwicky had proposed decades earlier and almost no one had taken. Seriously, every galaxy must be embedded inside an enormous invisible halo of additional mass, a halo extending far beyond the visible disk, supplying exactly the gravity needed to keep those outer stars locked in their orbits. But here is where it gets stranger. Rubin's galaxies and Zwicky's cluster were not isolated cases. As decades passed, independent lines of evidence kept arriving from completely different directions, each one pointing back to the same invisible conclusion. Astronomers studying the motion of entire galaxy clusters found the same mass discrepancy Zwicky had first measured. Astronomers studying gravitational lensing, the bending of background starlight around massive foreground objects, predicted directly by Einstein's general relativity, found that galaxies and clusters were bending light far more than their visible matter should allow. And astronomers mapping the large-scale structure of the universe found that the patterns of galaxy clustering only made sense if an unseen scaffold of mass had been guiding matter into place since the early universe. 3 independent methods, 3 different eras, 3 different teams of scientists, often working without knowledge of each other's results, all converging on the same impossible number. And then came the discovery that made the case almost impossible to argue against. In 2006, astronomers studying a distant system called the Bullet Cluster, officially named 1E0657-56, sitting approximately 3.8 billion light-years away, captured something extraordinary. The system was caught in the act of a violent collision. 2 massive galaxy clusters that had slammed through each other roughly 150 million years earlier, moving at speeds of several million miles an hour. 2 completely different instruments mapped 2 completely different things inside that collision. NASA's Chandra X-ray Observatory imaged the hot gas, the bulk of the cluster's ordinary visible matter, and revealed it concentrated in 2 glowing pink clouds near the center, dragged backward and shocked by the force of the impact, the way water piles up in front of a speeding boat. Separately, astronomers mapped where most of the gravitational mass actually sat, using weak gravitational lensing, the statistical distortion of background galaxy shapes caused by the bending of light around enormous concentrations of mass spread across the sky. That gravitational mass appeared in 2 entirely different locations. Blue clouds, sitting apart from the gas entirely, virtually undisturbed by the collision. The visible matter and the gravitational mass had separated. Ordinary matter collided, slowed down, and piled up exactly where physics predicted it should. But something else, something that did not interact with the collision at all, something that passed straight through the impact as if the other cluster wasn't even there, carried most of the gravity onward, undisturbed. That something could not be ordinary matter. It had to be something that interacts through gravity and essentially nothing else. The European Space Agency's Planck satellite, mapping the faint afterglow of the Big Bang with extraordinary precision, eventually gave us the most complete inventory of the universe's contents ever assembled. The numbers it returned are almost impossible to sit comfortably with. Ordinary matter, every star, every planet, every living thing, everything made of atoms, accounts for roughly 5% of the universe's total mass and energy. Dark matter accounts for approximately 27%, and the remainder, the dominant majority, belongs to something else entirely, a separate mystery we will need to confront directly before this story is finished. Sit with that fraction for a moment. For every single atom of ordinary matter in the cosmos, every proton inside every star, every neutron inside every planet, roughly 5 times more mass exists in a form that does not glow, does not block starlight, and has never been directly seen by any instrument ever built. Here's the thing most people don't realize. Dark matter is not simply hiding in the dark patches between galaxies, like some kind of cosmic filler. It functions as scaffolding. Cosmologists trace its story back to the universe's earliest moments, when tiny irregularities in the newborn cosmos caused dark matter to begin clumping together under its own gravity, forming dense gravitational wells long before ordinary gas could cool and concentrate on its own. Ordinary matter then fell into those wells afterward, drawn in by gravity, cooling, fragmenting, eventually igniting into the first stars. Standard cosmological models cannot reproduce the galaxies we actually observe without this invisible scaffolding doing the structural work first. Take the dark matter away, and the simulations simply fail to build anything resembling the universe we live in. This is what makes dark matter so strange. It built the architecture. We're living inside its blueprint, and we still do not know what it is, so scientists went looking for it directly. For decades, the leading candidate was a hypothetical particle called a WIMP, short for weakly interacting massive particle, a particle that would barely interact with ordinary matter at all, slipping through entire planets the way a ghost might slip through a wall, only occasionally bumping into an atomic nucleus and producing a flicker of detectable energy. To catch that flicker, physicists built detectors nearly a mile underground, shielded from cosmic rays, sealed inside ultra-clean materials designed to filter out every possible false signal. The most sensitive of these detectors, called LZ, has now collected data through April of 2025, the largest data set any dark matter experiment has ever assembled, and the result, so far, is silence. No confirmed WIMP interactions. Researchers have ruled out an enormous range of WIMP possibilities with unmatched precision, narrowing the hiding places considerably. But narrowing is not finding, and this is not the only candidate left standing. Physicists have proposed axions, extremely light, almost ghost-like particles originally invented to solve an unrelated puzzle in particle physics, which happen to also fit the profile dark matter requires. Others have proposed sterile neutrinos, ultralight scalar fields, and even primordial black holes formed in the first instance after the Big Bang. Each candidate carries its own constraints. Primordial black holes, for instance, cannot easily account for all of dark matter across most of the mass ranges scientists have tested, based on gravitational lensing surveys that would have detected far more of them if they existed in sufficient numbers. Collider experiments, meanwhile, search for dark matter indirectly, watching for missing momentum after particle collisions, energy that seems to vanish from the equation. But missing energy alone proves only that something escaped detection, not that the something is dark matter. A genuine scientific debate runs underneath all of this, and it deserves to be stated plainly rather than resolved. A minority of physicists argue that we may not need a new particle at all. Frameworks like modified Newtonian dynamics, or MOND, propose instead that gravity itself behaves differently at extremely low accelerations, removing the need for invisible mass altogether. MOND succeeds remarkably well at explaining flat rotation curves in individual galaxies, the very phenomenon Rubin first observed, but it struggles to explain galaxy clusters, gravitational lensing patterns, and the large-scale structure of the cosmos as convincingly as particle dark matter does, even with relativistic extensions designed to patch those gaps. Neither side has produced a complete victory. The tension remains genuinely unresolved within the scientific literature, and even within the favoured dark matter framework itself, certain stubborn puzzles persist at smaller scales. Discrepancies between simulated galaxies and observed ones, involving the detailed shape of dark matter halos and the number of small satellite galaxies we expect to find orbiting larger ones. Many researchers suspect these tensions can be resolved through better modelling of ordinary astrophysical feedback, the way exploding stars and active galactic cores can reshape a halo structure without abandoning cold dark matter altogether. Others remain unconvinced. The debate continues. Here is what remains. After Zwicky, after Rubin, after the Bullet Cluster, after Planck's inventory, after decades of underground detectors listening in silence nearly a mile beneath the Earth, we know with overwhelming observational confidence that something is there. Its gravitational fingerprint is written across every galaxy, every cluster, every strand of cosmic structure we have ever mapped. It outweighs ordinary matter more than 5 to 1. It built the scaffolding that allowed stars, planets, and eventually us to exist at all, and we still do not know what it is. Think about that for a moment. The dominant architect of the visible universe has never once been directly seen, touched, or captured in any laboratory on Earth. We have spent nearly a century chasing its shadow without once finding its source. But dark matter, mysterious as it is, was never the only invisible force at work, because in 1998, astronomers studying ancient exploding stars stumbled onto something that did not just challenge our understanding of what fills the universe, it challenged whether the universe's expansion was even slowing down at all. To understand how that challenge arrived, we need to understand the tool that delivered it, an exploding star known as a Type 1a supernova. A Type 1a supernova occurs when a dense stellar remnant called a white dwarf, a star roughly the mass of our Sun compressed down to a size comparable to Earth, pulls in extra material until it crosses a critical threshold and detonates in a runaway thermonuclear explosion. For a few brief weeks, that single explosion can outshine an entire galaxy of hundreds of billions of stars. Astronomers prize these events because they function as what scientists call standardized candles, objects whose intrinsic brightness is well enough understood that comparing how bright one appears from Earth reveals how far away it actually is, similar to judging the distance of a candle in the dark by how dim its flame looks from where you stand. Here's the thing, most people don't realize about that word standardized. These explosions are not naturally identical. Astronomers correct their measured brightness using empirically calibrated relationships between how fast a supernova's light fades and how luminous it truly was at its peak, a technique developed and refined over years of careful observational work. And honestly, the deeper physics of what triggers these explosions, the exact progenitor systems involved, the rate at which a companion star accretes onto the white dwarf, remains scientifically unsettled territory. Researchers suspect more than one explosion pathway is probably at work across different stars, but the standardization, hard-won and continuously refined, has held up. These remain among the most reliable distance markers we possess across billions of light years. By the 1990s, two competing teams of astronomers set out to use these standardized candles for the most ambitious purpose imaginable, measuring the entire history of cosmic expansion. Saul Perlmutter led a group called the Supernova Cosmology Project, based at Lawrence Berkeley National Laboratory. Brian Schmidt led a rival effort called the High-Z Supernova Search Team, with Adam Rees driving much of the critical analysis. Both teams were racing toward the same goal, using similar methods, often watching the same patch of sky for the faint, fleeting flare of a distant detonation. Both teams expected to confirm something everyone already believed. Since Einstein's general relativity first described an expanding universe, cosmologists had assumed that gravity, acting on all the matter scattered throughout space, must be gradually slowing that expansion down. Think of a ball thrown upward into the air. Gravity pulls against its motion the entire way, decelerating it continuously, whether it eventually falls back down or merely slows its climb. Cosmologists expected the universe to behave the same way, expanding outward from its hot origin, with the combined gravitational pull of every galaxy, every cluster, every particle of matter acting like a brake, gradually decelerating the expansion rate over billions of years. The two teams set out to measure exactly how much that braking had occurred. Their method was elegant. They compared two independent measurements for each distant supernova. First, the supernova's measured brightness, which reveals how far the light actually had to travel to reach Earth. Second, the redshift of its host galaxy, the stretching of light's wavelength caused by the expansion of space during the photon's journey, which reveals how much the universe has expanded since that light was emitted. If gravity were truly decelerating expansion the way everyone expected, distant supernovae viewed from far enough back in cosmic time should appear slightly brighter and closer than their redshift alone would suggest, because the expansion rate would have been faster in the past, before gravity had time to slow it down. That is not what either team found. The distant supernovae appeared fainter than the decelerating models predicted. Not brighter, fainter, meaning farther away than they should have been if expansion were simply coasting to a gradual stop. Brian Schmidt's reaction, when the data first came in, was disbelief. He assumed the result had to be an error, and he spent the following 6 weeks searching for the mistake that would make the anomaly disappear. He never found one. Both teams, working independently, with different instruments, different supernova samples, and different analysis pipelines, arrived at the same impossible conclusion. The universe's expansion was not slowing down, it was speeding up, and that single sentence demanded years of grueling skepticism before anyone, including the scientists who discovered it, would trust it. Could interstellar dust be dimming the distant supernovae, mimicking the appearance of greater distance? Researchers tested for it and found the dimming pattern didn't match dust's known behavior. Could ancient supernovae simply explode differently than nearby ones, evolving in luminosity across cosmic time in a way that would corrupt the standardization? Years of follow-up studies probed that possibility too. Could selection effects be quietly biasing which distant supernovae astronomers could even detect in the first place? Each objection got tested. Each one failed to explain away the signal. By 1998, both teams published independently, and the case held. Here is where the story cracks open into something genuinely strange. If gravity pulls everything together, and the universe's expansion is accelerating instead of decelerating, then some kind of repulsive influence must be working against gravity itself on a cosmic scale, throughout the entirety of space. Scientists needed a name for it, and the name they chose was deliberately, almost uncomfortably honest about how little they understood. They called it dark energy, not because anyone had identified what it actually is, simply because something was driving accelerated expansion, and that something remained, and still remains, entirely undetected by any direct measurement. The simplest mathematical description came from a term Einstein himself had added to his original equations decades earlier, called the cosmological constant, a representation of a constant energy density filling all of space uniformly, producing a steady negative pressure that pushes space outward rather than pulling it inward. It's worth being careful here, because the popular legend claims Einstein later called this term his biggest blunder. The documented history is messier and less tidy than that story suggests, but the term itself, regardless of its complicated path through Einstein's own thinking, turned out to fit the supernova data remarkably well decades later. One natural candidate for what fills that cosmological constant is the quantum vacuum itself, the idea that even completely empty space, devoid of any particles, still seethes with brief fluctuating bursts of energy permitted by quantum field theory. Physicists can measure certain effects of these quantum field fluctuations in carefully controlled laboratory settings, but when theorists tried calculating the vacuum's total expected energy density from first principles and compared it to what the accelerating universe actually requires, the mismatch was almost beyond description. The theoretical prediction came out staggeringly larger than the observed value, a problem so severe that physicists simply call it, without exaggeration, the cosmological constant problem. It remains one of the most significant unsolved tensions between quantum theory and gravitational physics, and there's a second strangeness layered on top of the first. Dark energy's influence has only become dominant relatively recently in cosmic history, just as matter density thinned out enough from expansion to let it take over. Scientists call this the coincidence problem, the puzzling fact that we happen to be observing the universe during the specific era when dark energy's dominance over matter is becoming apparent rather than billions of years earlier or later. No accepted explanation resolves why our cosmic moment lines up this way. Naturally, the cosmological constant is not the only model on the table. Some physicists favor quintessence, theoretical models in which dark energy isn't a fixed, unchanging density at all, but instead behaves like a dynamic field that evolves slowly across cosmic time, its strength shifting as the universe ages. Others have proposed phantom energy, a more extreme variant requiring properties that, if real, could eventually rip every bound structure in the universe apart, though this scenario depends on specific theoretical assumptions about dark energy's behavior that remain entirely unconfirmed by current data. And a separate camp argues the entire premise might be backward, that we don't need a new form of energy at all, but rather a modification to how gravity itself behaves across enormous cosmic distances, eliminating the need for a mysterious accelerating substance altogether. None of these camps has won. The scientific debate remains genuinely open. For years, the simplest model, Einstein's unchanging cosmological constant, combined with cold dark matter, forming what cosmologists call the lambda-CDM model, fit the accumulated evidence beautifully. The European Space Agency's Planck satellite, refining its measurements of the universe's afterglow, settled on dark energy, constituting approximately 68% of the universe's total mass and energy content, the dominant majority of everything that exists. But then came a result that shook that confidence. Between 2024 and 2025, an instrument called the Dark Energy Spectroscopic Instrument, mounted on a telescope at Kitt Peak in Arizona, completed its first 3 years of observation, ultimately mapping the precise locations of over 14 million galaxies and quasars, the largest three-dimensional map of the universe ever constructed. DESI measured a phenomenon called baryon acoustic oscillations, faint ring-shaped imprints, left in the distribution of matter by sound waves rippling through the hot early universe, which now serve as a kind of cosmic ruler for tracking how cosmic distances have evolved over roughly 11 billion years. When DESI's results were combined with independent measurements from the cosmic microwave background, supernova catalogues, and gravitational lensing surveys, something unexpected emerged. The combined data fit a model where dark energy's strength changes over time, noticeably better than it fit the standard, unchanging cosmological constant in some combinations of data sets by a statistical margin as strong as 4.2 standard deviations, a level that approaches, but does not yet reach, the 5 standard deviation threshold physicists typically require to call something a confirmed discovery. This was not a small ripple in the data. This was, in the words of researchers who had spent years building the standard cosmological picture, a result that shook the field. And yet caution remains essential here, because that statistical significance shifts depending on exactly which supernova catalogue gets used, which mathematical parameterization describes the possible time evolution of dark energy, and which calibration assumptions enter the analysis. Change those choices, and the strength of the signal moves with them. So let's be precise about where this actually leaves us. Evolving dark energy is currently a powerful, repeatedly reinforced hint sitting inside the data. It is not yet an established replacement for the standard lambda-CDM model. Both possibilities remain genuinely alive in the scientific literature, and serious researchers occupy both camps. And dark energy's possible evolution is not the only crack currently running through our model of cosmic expansion. A separate, long-standing puzzle called the Hubble tension continues to resist resolution. Measurements of the universe's current expansion rate taken from the nearby local universe, using calibrated supernovae and other distance markers, consistently produce a value of approximately 73 kilometers per second for every megaparsec of distance, a megaparsec being roughly 3.26 million light-years. Measurements derived from the cosmic microwave background, projecting the early universe's known physics forward through 13.8 billion years of cosmic history, consistently produce a noticeably lower value, close to 67 kilometers per second per megaparsec. Picture two separate teams of surveyors, each using a different but individually reliable method, measuring the exact same stretch of coastline and arriving at meaningfully different lengths every single time. That is the Hubble tension in its simplest form, and improved instruments, including the James Webb Space Telescope, have only sharpened the disagreement rather than resolving it. No single proposed fix, modified dark energy, altered early universe physics, new particle interactions, currently explains both the Hubble tension and the full pattern of cosmic structure growth simultaneously. Researchers studying this carefully describe it as a multi-dimensional problem, not a clean discrepancy with one tidy cause waiting to be found. Step back from the statistics for a moment, because here is what all of this actually means for the universe you live inside. The void between galaxies is not a fixed backdrop, holding still while matter drifts through it. The separations themselves, between every unbound galaxy, every cluster, every supercluster across the observable universe, are actively growing, and the rate at which they grow has been increasing for billions of years, driven by a component that outweighs every star, every planet, every form of matter combined, and that no instrument on Earth has ever directly detected. We measured this acceleration through the brief, brilliant deaths of stars billions of light-years away, light that began its journey across the cosmos long before our own solar system finished forming, and what that ancient light revealed continues to deepen the longer scientists study it, rather than settling into something simple and resolved. Here is the disturbing part. Emptiness in this universe is not a static condition waiting patiently in the background, while the interesting things happen elsewhere. Emptiness is the active, accelerating force shaping everything that will ever happen to every galaxy, every star, and every observer who exists to notice it. The space between things is winning, and the rate at which it's winning may itself be changing in ways our most advanced instruments have only begun to detect. But to understand exactly what that means for the galaxies we can currently see, for the structures filling the cosmic landscape around us, and for the staggering territories of darkness that occupy nearly all of that landscape, we need to look at the actual architecture those separations are carving into existence. Because the universe is not simply emptying uniformly in every direction, it is emptying into a shape, and that shape has a name scientists never expected to need. For most of human history, the night sky was the only map astronomers had, and it was a flat one. Every star and galaxy appeared painted onto a single distant surface, with no way to tell which light sat nearby and which sat unimaginably farther back. But starting in the late 1970s and accelerating through the decades that followed, astronomers began conducting what are called redshift surveys, large-scale efforts to measure not just where galaxies appear in the sky, but how far away each one actually is, using the stretching of their light, caused by cosmic expansion, as a distance marker. That single addition changed everything. Once astronomers could plot galaxies in 3 dimensions instead of 2, the flat, scattered sky resolved into something startling. The galaxies were not scattered randomly throughout space. They were arranged. Picture not a haze of stars suspended evenly through the dark, but something closer to dew clinging to a spider's web. After a cold night, beads of moisture gathered along threads, clustered thickly at every junction, with vast, clear gaps stretching between the strands. Astronomers call this structure the cosmic web. Galaxies cluster into dense knots called nodes, stretch out along long connective filaments, gather into broad, sheet-like walls, and leave enormous gaps in between, where almost nothing exists at all. Here's what makes this even stranger. The galaxies themselves, with all their light and stars and planets, are not actually the architects of this structure. Dark matter, the invisible scaffolding we already traced back to Zwicky and Rubin, forms the underlying skeleton of the entire web, with diffuse intergalactic gas tracing its outline. The luminous galaxies we can actually see are essentially decorations, gathering wherever that invisible structure happens to concentrate enough gravity to pull ordinary matter into place. And the gaps in that web are not minor. They are called cosmic voids, vast underdense regions containing dramatically fewer galaxies than a typical patch of space their size should hold. These are not failed patches of nothing. They are real, measured regions where the universe's matter simply declined to gather. Here's a fact that should stop you for a moment. Voids occupy roughly 80% of the observable universe's volume. Picture a sponge. The solid material, the part that actually holds shape and structure, makes up only a small fraction of the object, while the rest is empty pockets of air. Run your finger across a kitchen sponge sometime and notice how much of what you're touching is actually nothing at all. The cosmic web works the same way, except the proportions are even more extreme, and the solid portions, the filaments and nodes, contain a wildly disproportionate share of all the matter that exists. In 1981, an astronomer named Robert Kirshner, working with colleagues at the University of Michigan, was using exactly this kind of redshift survey to build a 3-dimensional map of galaxies in the direction of the constellation Boötes. As the map filled in, something strange appeared. At a distance of roughly 700 million light-years from Earth, an entire region of the map simply went blank. Kirshner's team initially found only a handful of galaxies scattered across that region. Follow-up surveys eventually located a total of about 60. For a region of space this size, astronomers calculate there should have been somewhere around 2,000. Astronomer Greg Aldring later offered a way to feel the scale of that absence. If the Milky Way itself had formed at the center of this void, we would not have detected the existence of other galaxies until well into the 20th century, simply because there would have been nothing nearby bright enough to notice. This region became known as the Boötes Void, sometimes called the Great Nothing. Its diameter spans somewhere between approximately 250 and 330 million light-years, depending on which survey and method you consult, since a void's edge is less a sharp wall and more a gradual thinning that resists a single precise boundary. Even using the more conservative figure, an object the size of our Milky Way galaxy, at 100,000 light-years across, could fit inside that void several thousand times over. But let's be precise about what void actually means here, because the name oversells it. The Boötes void is not a true vacuum, scraped clean of everything. It contains dozens of confirmed galaxies, faint matter, and diffuse gas. It is dramatically underpopulated, rather than swept empty, and that distinction matters enormously for what comes next. So what would it actually be like to live inside one of these regions? Imagine you were born on a planet orbiting a star somewhere deep inside a void like Boötes. Looking up at your night sky, you would still see your own galaxy's stars scattered normally overhead. Nothing about your immediate neighborhood would feel unusual. But beyond that, where someone on Earth sees the faint smudges of neighboring galaxies and, with a strong enough telescope, traces the glittering architecture of countless more, your sky would offer almost nothing. a profoundly poorer extragalactic vista, stretching for hundreds of millions of light years in every direction, with only the rare, isolated galaxy breaking the silence. Strangely, that isolation makes void galaxies scientifically valuable rather than simply lonely. Without nearby neighbors to collide with, merge with, or gravitationally disturb, galaxies inside voids serve as isolated laboratories, letting astronomers study how a galaxy evolves when left almost entirely alone, away from the violent mergers and interactions that reshape galaxies in busier environments. Some void galaxies have preserved unusually pristine, primitive characteristics, specifically because nothing nearby has ever disturbed them. But voids reach further than astronomers initially expected. In 2015, researchers identified an enormous underdense region called the Eridanus supervoid, sitting in the same direction as one of the most peculiar features ever found in the cosmic microwave background, a patch of sky cooler than its surroundings, known simply as the cold spot. The logic seemed elegant. Light crossing a void loses a small amount of energy as it climbs out of a slightly shallower gravitational landscape, an effect called the integrated Sachs-Wolf effect, which could plausibly chill the background radiation passing through it. Except something was wrong with the numbers. When researchers calculated how much cooling the Eridanus supervoid should actually produce under the standard cosmological model, the void could only account for roughly 10 to 20% of the cold spot's full temperature drop. The void is real. The alignment is real. But the void alone cannot explain what we're measuring. A genuine scientific debate continues over whether some part of our cosmological model needs revision to close that gap, or whether the cold spot results from some combination of factors we haven't fully isolated yet. And let's be clear about one popular alternative explanation you may have encountered. Claims that the cold spot represents evidence of a collision with another universe belong to speculative fringe territory, not anything close to mainstream evidence-supported cosmology. Here's the thing most people don't realize. We don't have to travel anywhere to find one of these structures. Our own Milky Way sits along the edge of a region called the local void, a vast underdense zone immediately adjacent to the thin sheet of galaxies that contains our own galactic neighborhood. Researchers using a survey called Cosmic Flows 3 mapped the motion of galaxies across our cosmic vicinity and discovered something that initially looked like it violated intuition. Our galaxy isn't just drifting through space randomly, it's being pushed. Here's how that's possible without anything physically touching us. Gravity pulls matter toward denser regions and, in relative terms, away from emptier ones. Not because the void itself exerts some mysterious repulsive force, but because the surrounding overdense regions, dense with galaxies and dark matter, are pulling everything nearby toward themselves, leaving the void looking, from our perspective, like it's pushing outward. Researchers identified this effect partly through what they named the dipole repeller, a basin of low density whose surrounding gravitational pulls account for roughly half of the Milky Way's total measured motion through the cosmos. We are, at this very moment, drifting away from emptiness and toward the densely populated Shapley concentration, a massive collection of galaxy clusters pulling much of our local cosmic neighborhood toward it. This is not a passive backdrop. This is an active gravitational tug-of-war, and we are inside it. This pattern of overdense regions gaining matter, while underdense regions lose it, is not a coincidence. It is the entire mechanism by which the cosmic web came to exist in the first place. Trace it back far enough, and the universe's earliest matter distribution was almost perfectly smooth, with only the faintest irregularities, tiny density differences seeded in the universe's first instance. Regions with slightly more matter than average exerted slightly stronger gravity, pulling in still more matter from their surroundings. Regions with slightly less matter exerted slightly weaker gravity and lost ground in the competition. Across billions of years, that tiny initial imbalance compounded, the way a small head start in a foot race widens steadily into an unbridgeable gap the longer the race continues. The rich got richer, the empty got emptier, and then dark energy entered the competition. As we already traced, dark energy's accelerating push works specifically against the clumping that gravity tries to achieve, actively suppressing the growth of new structure in the present and future universe, while simultaneously stretching the distances between everything not gravitationally bound together. The voids are not simply staying empty, they are actively, continuously emptying further, even now as the filaments around them grow correspondingly denser and more defined. But here's an important distinction we need to make before this goes any further, because it's the single most common misunderstanding about cosmic expansion. This stretching does not apply to everything uniformly. Your body is not expanding. The solar system is not expanding. Atoms are not expanding. Cosmological expansion only dominates at scales where gravity and the other fundamental forces have become too weak to resist it, meaning bound systems like galaxies, stars, planets, and people remain held together by forces that simply overwhelm the comparatively gentle push of cosmic expansion at small scales. The emptying we're describing belongs entirely to the unbound intergalactic scale, the vast spaces between galaxies that share no gravitational bond strong enough to hold them. And this is precisely the landscape the most ambitious sky mapping missions in human history are now racing to chart with unprecedented precision. The European Space Agency's Euclid mission, launched specifically to investigate dark matter and dark energy, released its first major batch of survey data in March of 2025. In just 1 week of observing 3 preview regions of sky, Euclid had already detected 26 million galaxies, some as distant as 10.5 billion light-years away. Over the coming years, the mission plans to measure the precise shapes of well over 1 billion galaxies across 10 billion years of cosmic history, mapping the 3-dimensional structure of dark matter with a level of detail no previous survey has achieved. 26 million galaxies captured in a single week, scanning a sliver of sky representing a small fraction of Euclid's eventual full survey. Sit with that number for a moment, because it sounds like proof of an unimaginably crowded universe. But here is the deeper truth those staggering galaxy counts actually confirm once you place them back into their proper 3-dimensional context. Those millions upon millions of galaxies, magnificent as they are, still cluster along the same thin web-like filaments and walls we've been tracing this entire chapter. The overwhelming majority of the volume surrounding them, the 80% of cosmic space we already established, remains comparatively starved of galaxies entirely. More galaxies discovered does not mean a fuller universe. It means a more precisely mapped portrait of exactly how unevenly distributed the universe's contents really are. Here's a question worth sitting with before we move forward. We live inside the local sheet, a comparatively structured region threaded with galaxies, pulled steadily toward denser concentrations, positioned where the cosmic architecture happens to be relatively rich. Our intuitive sense of a universe filled with galaxies, walls, and structure comes specifically from occupying one of the better populated neighborhoods this cosmic web has to offer. What we now understand is that this feeling of abundance was never the universe's default condition. It was a local privilege of address, because for every filament dense enough to build a galaxy, for every node massive enough to host a cluster, for every wall thick enough to hold a supercluster together, an equivalent void exists somewhere else in the cosmic web, hollowed out by the exact same gravitational process that built the structure around us. The voids are not failures of cosmic architecture. They are the architecture's necessary counterpart, written into existence by the same physics that made our own galaxy, our solar system, and everyone who has ever looked up and wondered what fills the dark spaces between the stars. But knowing that the voids are growing, and knowing that the distances inside them are accelerating, leaves one question still completely unanswered. If space itself keeps stretching, if galaxies keep racing away from each other faster with each passing era, then what does the universe's horizon actually look like from where we stand right now? And more unsettling still, how much of what we can currently see might already be slipping permanently beyond our reach? Let's be precise about what we mean because this is the single most misunderstood concept in all of cosmology, and getting it wrong distorts everything that follows. The universe is not expanding the way an explosion expands outward into surrounding empty space, with debris flying away from some central point into a void that was already there waiting to receive it. That image, however natural it feels, is simply not what's happening. Cosmological expansion means the distances within space-time itself are increasing. Space is not a stage on which galaxies move apart. Space is the thing that is stretching, carrying galaxies along with it, the way raisins embedded in a rising loaf of bread drift farther apart from each other as the dough itself expands, without any single raisin actually moving through the bread toward an edge. That analogy, like every analogy in physics, has limits worth naming honestly. Cosmologists also commonly use a balloon surface, with dots drawn on it representing galaxies, spreading apart as the balloon inflates. It's a useful picture, but a balloon surface is only two-dimensional, curved in a way our actual three-dimensional universe isn't necessarily required to be, and the balloon itself expands into surrounding air, which has no equivalent for our universe expanding into anything external. Use these images to build intuition, not to describe the full truth. In the 1920s, Edwin Hubble, building on theoretical work by Georges Lemaitre, discovered a striking pattern. The farther away a galaxy sits, the faster it appears to be receding from us. This relationship, now called the Hubble-Lemaitre law, reveals something specific about the structure of our cosmos. It's not that distant galaxies are flying through space faster than nearby ones. It's that more space exists between us and them, so more of that space is stretching simultaneously, compounding into a greater overall recession speed. This stretching produces a phenomenon called cosmological redshift. As light travels across expanding space on its journey toward us, the space itself stretches during transit, and the light's wavelength stretches right along with it, shifting toward the longer, redder end of the spectrum. The longer light travels, the more space it crosses, and the more pronounced that redshift becomes. This is fundamentally different from a galaxy's local peculiar motion, its individual gravitational drift relative to its neighbours, which produces its own separate, comparatively modest redshift or blue shift. Large-scale cosmological redshift comes from the geometry of the universe itself, evolving during the light's entire journey. Here's where the story gets genuinely strange, and where many people's intuition runs straight into trouble. If recession speed increases with distance, then sufficiently distant galaxies must, at some point, be receding from us faster than the speed of light itself. That sounds like it directly violates Einstein's special relativity, which firmly states that nothing can travel faster than light through space. But here's the resolution, and it's worth sitting with carefully. Special relativity's speed limit applies to objects moving through space. It says nothing about how quickly space itself can expand. A galaxy at extreme distance isn't rocketing through the universe at superluminal speed. The space between us and that galaxy is simply growing fast enough that the total separation increases faster than light could cross it. Nothing local is being violated. The rule simply doesn't apply to a quantity that was never about local motion in the first place. This distinction gives rise to several genuinely different boundaries in the sky, and conflating them is probably the most common error in popular explanations of cosmology. The Hubble sphere marks the distance at which a galaxy's recession speed, due to cosmic expansion alone, exactly equals the speed of light, currently sitting at approximately 14.4 billion light-years from Earth. The particle horizon marks the absolute farthest distance from which light has had time to reach us since the universe began, currently around 46.5 billion light-years away, accounting for how much the universe has expanded during each photon's entire journey. And the cosmic event horizon marks something else entirely, the boundary beyond which light emitted right now, from this very moment forward, could never reach us, no matter how long we waited, currently estimated at somewhere between 16 and 18 billion light-years away. Here's the part that surprises almost everyone first encountering this. A galaxy can sit beyond the Hubble sphere, currently receding faster than light due to cosmic expansion, and we can still see it. We are seeing light it emitted long ago, even if that galaxy's recession speed was already past the light speed threshold, because the expanding Hubble sphere eventually overtook the incoming photons. The light has been travelling toward us this entire time, even as the space behind it kept stretching. Crossing the Hubble sphere doesn't switch off a galaxy's visibility. It only means we are now seeing it as it appeared in an earlier, less distant chapter of cosmic history. So let's be careful with a claim that gets repeated constantly and isn't quite accurate. Not everything beyond the Hubble sphere is already permanently lost to us. Some of that light is still arriving, still crossing the gap, still telling us a true story about a galaxy that, by now, has likely receded much farther away than the light suggests. But here's where the suspense deepens, because that visibility is not permanent. As cosmic acceleration continues, unbound galaxies, meaning galaxies with no gravitational tether holding them to us, will eventually cross the cosmic event horizon for good. Their light won't simply vanish in an instant. It will fade gradually, redshifting further and further as expansion continues stretching every photon already in transit, growing dimmer and arriving at our telescopes at an ever-decreasing rate until eventually it crosses a threshold so extreme that no instrument, however sensitive, could ever recover a usable signal. Think about that for a moment. We are not watching galaxies disappear. We are watching them fade into silence, the way a radio signal weakens and dissolves into static the farther a car drives from the transmitting tower. Except this fade never reverses and never ends. And here's the genuine complication layered underneath all of this. Not everything in the universe is subject to this fading future. Gravitationally bound structures, meaning systems held together by forces stronger than the gentle pull of cosmic expansion at their scale, simply do not separate the way unbound galaxies do. Your body holds together. The solar system holds together. And entire galaxies, and even groups of galaxies bound tightly enough by mutual gravity, hold together too. Our own Milky Way provides the clearest example. For decades, the standard story held that the Milky Way and the Andromeda Galaxy were on a guaranteed collision course, destined to merge into a single larger galaxy in roughly 4 to 4.5 billion years. But here's where a genuine scientific debate enters the picture. A 2025 study published in Nature Astronomy, incorporating updated position, velocity, and mass measurements from the Hubble Space Telescope and the Gaia mission, found the outcome to be considerably less certain than the old story suggested. Depending on which nearby galaxies are factored into the simulation, particularly the Triangulum Galaxy and the Large Magellanic Cloud, researchers calculated the odds of an actual collision within the next 10 billion years at roughly 50-50. If a merger does occur, the researchers suggest it's more likely to happen 7 to 8 billion years from now rather than 4. The conventional, confident, inevitable collision story you may have heard before is, according to this newer analysis, considerably more uncertain than it once seemed. Scientists studying our own galactic future do not yet agree on this outcome, and that disagreement is itself part of the honest scientific picture. Whatever ultimately happens between these two galaxies, the broader pattern holds. Our local group, the modest collection of galaxies gravitationally bound to our own, will likely remain together long after every external unbound galaxy has redshifted into undetectable silence. We will become an isolated island, anchored together by gravity, surrounded by an empty, darkening sky. And here's a detail worth correcting before it slips by unnoticed. Even structures significantly larger than our local group, the enormous superclusters astronomers map across hundreds of millions of light years, are generally not single gravitationally bound systems at all. They are loosely associated regions where the cosmic web happens to be denser, but most of their components remain unbound, subject to exactly the same accelerating separation as every other unbound galaxy in the cosmos. Here's where this story reaches its most unsettling implication, and it concerns something far older than any galaxy: the cosmic microwave background itself, the faint afterglow radiation left over from the universe's hot, early infancy, currently our single most important piece of evidence for the entire Big Bang framework. In a detailed 2007 analysis published in the journal General Relativity and Gravitation, physicists Lawrence Krauss and Robert Scherer extrapolated our current cosmological model forward in time and reached a conclusion that should unsettle anyone who has ever found comfort in scientific certainty. The cosmic microwave background will not last forever as detectable evidence. As cosmic expansion continues accelerating, that ancient radiation will keep redshifting and cooling, its characteristic wavelength stretching dramatically longer, and its intensity dropping by many orders of magnitude. Krauss and Scherer calculated that by roughly 100 billion years from now, the background radiation will have stretched and faded to the point of becoming completely undetectable by any plausible future instrument. Stack the implications, because they compound quickly. The cosmic microwave background, our clearest direct evidence for the hot Big Bang, gone. Evidence of the primordial elements forged in the universe's first minutes, increasingly scrambled and reprocessed beyond recognition after eons of stellar fusion and recycling. Evidence of the Hubble expansion itself, the very phenomenon revealing that the universe has a history at all, gone too, once every external galaxy has redshifted into permanent silence and only our own bound local group remains visible. A civilization arising in that unimaginably distant future, looking outward from inside its own isolated island, surrounded by an unchanging starlit darkness, would have every reason to conclude they live inside a small, static, eternal universe. Not because they failed at science, because the evidence required to conclude otherwise will have genuinely, physically disappeared. Sit with that, because here is the question it forces upon us. If a future universe can lose access to evidence this fundamental, what does that say about the evidence we're currently working with? Here's the honest answer science actually provides. We don't know what we might already be missing. We cannot rule out that some signature of the universe's earliest moments, something that might have resolved questions we are still actively debating, has already redshifted beyond any possibility of detection. We are limited specifically to the evidence currently within our reach, and that evidence, however extraordinary, was never guaranteed to be complete. And here's where this connects directly back to a tension we've already encountered. The Hubble tension, the persistent disagreement between local expansion rate measurements clustering near 73 kilometers per second per megaparsec and early universe measurements clustering closer to 67, remains stubbornly unresolved even with our most advanced instruments, including the James Webb Space Telescope. That disagreement is not simply an annoying technical detail. It's a signal that something about our understanding of cosmic expansion's full history likely remains incomplete, whether through unaccounted systematic errors or through genuinely new physics we haven't yet identified. But here is the reveal that should genuinely reframe everything you've just learned. We happen to be observing the universe during an extraordinarily favorable era, early enough that distant galaxies remain visible, their ancient light still arriving, still crossing the gap before acceleration carries them beyond reach, late enough that the universe has cooled and become transparent, allowing light to travel freely across cosmic distances at all, unlike the hot, opaque plasma that filled the universe's first few 100,000 years, when no photon could travel far before scattering off free-floating particles. We are living inside a narrow, privileged window between an opaque, unreadable past and an isolated, darkened future. This is not evidence that humanity occupies some specially chosen moment in cosmic history, the way ancient cosmologies once imagined Earth at the center of creation. It is simply a selection effect. Any observer capable of doing cosmology at all must necessarily exist during the relatively narrow span when galaxies remain visible and light still arrives faithfully from across the cosmic web. We are not chosen. We are simply currently positioned where the looking is still possible. Here is the picture that emerges from everything this chapter has revealed, and it deserves to land with its full weight. The universe is expanding outward, every moment, in every direction, accelerating as it goes. But our accessible window onto that universe, the portion of it we can actually study, measure, and understand, is doing the opposite. It is contracting inward, galaxy by galaxy, photon by photon, as one after another slips beyond the threshold where their light can ever reach us again. We are not simply watching the universe grow emptier around us. We are watching our own ability to witness that emptiness slowly, irreversibly, close. And that single realization demands we go back even further than Hubble, even further than the cosmic microwave background itself, to the very first fraction of a second after everything began. Because if the structures we see today, the galaxies, the voids, the entire architecture of emptiness we've spent this journey uncovering, all trace back to something seeded in that first instant, then understanding why the universe is empty requires understanding something far stranger. It requires understanding what was happening before there was anything to be empty at all. Strip away everything we've discussed so far. No galaxies, no stars, no atoms even. Travel back far enough, and you arrive at a universe that was simply a searing, featureless soup, far too hot and far too dense for anything resembling matter, as we know it to exist in stable form. In the earliest fractions of a second, quarks, the fundamental particles that eventually build protons and neutrons, were too energetic to bind together at all, drifting freely through a plasma so hot that the strong nuclear force couldn't yet hold them into the stable particles you're made of. As the universe expanded and cooled, those quarks locked into protons and neutrons, an event physicists call quark confinement, the moment matter took its first lasting recognizable form. Within the universe's first few minutes, conditions cooled just enough for those protons and neutrons to begin fusing into the lightest atomic nuclei, primarily hydrogen and helium, a process called primordial nucleosynthesis. This is where the universe's basic chemical inventory was set, locking in proportions of hydrogen and helium that astronomers still measure in ancient stars today as a direct test of the model. But matter still wasn't done becoming itself. For the next several 100,000 years, the universe remained a hot, ionized plasma, electrons and nuclei drifting separately, with light unable to travel freely because photons kept scattering off the loose, charged particles crowding every direction. Imagine trying to see across a thick fog. The light exists, but it can't travel in a straight line for more than a short distance before bouncing off some obstruction. That was the entire universe, for its first few 100,000 years. Then, approximately 380,000 years after the hot Big Bang, the universe cooled enough for electrons to finally bind permanently to nuclei, forming neutral atoms in an event cosmologists call recombination. With no more loose charge particles to scatter against, photons suddenly had a clear path. Light that had been trapped in that ancient fog broke free and began streaming outward in every direction, uninterrupted, for the first time in the universe's history. That liberated light is still traveling today. We detect it now as the cosmic microwave background, the faint, ancient radiation we've already encountered earlier in this journey, stretched by billions of years of cosmic expansion from a blistering glow into the cold microwave hum filling every direction of the sky. Here's what makes that ancient light so valuable. When astronomers map its temperature across the sky with extraordinary precision, they find it remarkably uniform, the same to roughly 1 part in 100,000, no matter which direction they look. Picture taking a temperature reading across an entire ocean and finding every single measurement matching to within an almost unmeasurable fraction of a degree. That's the kind of uniformity we're talking about. But within that overwhelming sameness, faint variations do exist. Tiny temperature differences smaller than that 1 part in 100,000 threshold, scattered across the sky like the faintest possible texture on an otherwise smooth surface. Those tiny variations are not noise. They are, as we're about to discover, the original fingerprints of everything that followed. But before we get to what those fingerprints became, we need to sit with a problem that genuinely troubled cosmologists for decades, because the uniformity itself shouldn't have been possible. Here's the issue. Light even travelling at its maximum possible speed, can only connect 2 points if there's been enough time since the beginning of the universe for it to travel between them. Calculate how large a single causally connected patch of the early universe could have been by the time recombination occurred, and you get a region far smaller than the full sky we observe the cosmic microwave background across today. In other words, regions of the sky that appear at nearly identical temperatures were never in contact with each other. They never had time to exchange so much as a single photon to equalize their temperatures, and yet they match to 1 part in 100,000 across regions that, by every standard calculation, should never have had the chance to coordinate at all. Cosmologists call this the horizon problem, and it sat as a genuine unresolved puzzle in the standard Big Bang picture for years. It wasn't alone. A second puzzle, called the flatness problem, compounded the mystery. When astronomers measure the universe's overall geometric curvature, meaning whether parallel lines drawn across the cosmos eventually converge, diverge, or stay perfectly parallel, the answer comes back astonishingly close to flat, perfectly parallel, accurate to within a fraction of a percent. Left to ordinary physics, any tiny deviation from perfect flatness in the universe's first moments should have compounded dramatically over billions of years of expansion, the same way a small error in a ship's initial heading widens into an enormous navigational mistake the farther it sails. For the universe to remain this close to flat after 13.8 billion years, its initial flatness would have needed to be tuned to an almost unbelievable precision. 2 separate puzzles, 2 pieces of evidence that the standard picture, on its own, simply couldn't explain. Here's where the story cracks open into something that should feel almost impossible. What if, in an unimaginably brief moment, right after the Big Bang, the universe underwent a period of extraordinarily rapid expansion, far faster than anything that followed, stretching space itself so dramatically that a single small causally connected patch grew large enough to encompass everything we can currently observe. This is cosmic inflation, the leading framework cosmologists use to address both problems simultaneously. If a tiny region, small enough that light had already equalized its temperature throughout, got stretched by this rapid expansion into something vast enough to become our entire observable universe, the horizon problem dissolves. The matching temperatures aren't a coincidence. They're a relic of a time before that explosive stretching, when everything genuinely was close enough to share the same temperature. And the same mechanism solves the flatness problem too. Imagine a small wrinkle on a balloon's surface, stretched flat the instant the balloon inflates to the size of a planet. Whatever curvature the universe carried before inflation, that same explosive stretching would have flattened it dramatically, driving it toward the near-perfect flatness we measure today, regardless of where it started. One mechanism, 2 previously unexplained observations, both resolved by the same proposed event. But here's something that needs stating honestly before we go further, because precision matters enormously here. We have not directly witnessed inflation occurring. No instrument has captured it in the act. Inflation remains a theoretical framework, supported by an inflaton-like field, a hypothetical form of energy proposed to drive that rapid expansion, but never yet confirmed through direct experimental detection of any associated particle. What inflation does offer, however, is a remarkably successful set of testable predictions, and that's precisely what has kept it the leading framework for decades. First, it predicts the near flatness we've already discussed. Second, it predicts that the universe's density fluctuations should be adiabatic, meaning all types of matter and radiation vary together in the same proportions rather than independently, exactly the pattern astronomers measure in the cosmic microwave background. And third, inflation predicts those fluctuations should be nearly scale invariant, meaning roughly the same strength whether you're examining tiny patches of sky or enormous ones, a remarkably specific prediction that detailed measurements from the Planck satellite have confirmed, with the spectral index landing extremely close to the predicted value. Here's the mechanism connecting all of this to the empty universe we've spent this entire journey exploring. During inflation's rapid expansion, tiny quantum fluctuations, the same kind of microscopic uncertainty that governs particle behavior at the smallest measurable scales, got stretched from subatomic dimensions into fluctuations spanning enormous cosmic distances. Those stretched fluctuations became the seeds for everything that followed. Once inflation ended, in a process called reheating, the tremendous energy driving that rapid expansion converted into the particles and radiation that filled the early universe, setting the stage for everything we've already traced: quark confinement, nuclear synthesis, recombination, and the cosmic microwave background itself, and those tiny fluctuations imprinted directly into the cosmic microwave background's faint 1 part in 100,000 temperature variations, which we already established earlier in this very chapter. Regions that were ever so slightly denser than average began attracting marginally more matter through gravity, a small initial advantage compounding through what's effectively positive feedback. Regions ever so slightly less dense lost matter comparatively, gradually emptying further as their denser neighbours pulled material away. Dark matter, already clumping gravitationally before ordinary matter had even finished decoupling from radiation, amplified this entire process, providing the scaffolding that let ordinary gas collapse into stars and galaxies far more efficiently than it could have managed alone. Every galaxy, every cluster, every filament threading the cosmic web, every void we've spent this journey mapping, all of it traces directly back to those faint temperature variations imprinted across the infant universe, which themselves trace back to quantum fluctuations stretched to cosmic scale during inflation's brief, explosive moment. But let's be honest about exactly how settled this picture actually is, because real scientific tension exists here, and it deserves to be stated plainly rather than smoothed over. Inflation is not one single theory. It's a broad framework encompassing dozens of competing specific models, each proposing different details about the hypothetical inflaton field's behavior. The Planck satellite's most recent detailed analysis has ruled out several of the simplest proposed models, including versions with a particular type of energy curve called a quadratic potential, while leaving numerous more complex alternatives entirely viable. The field hasn't converged on a single winning model. It's narrowed the field considerably while leaving genuine competition intact, and one of the most decisive potential tests remains stubbornly out of reach. Inflation predicts that the same rapid expansion should have generated primordial gravitational waves, ripples in space-time itself stretched to cosmic scale, which would leave a distinctive signature in the polarization pattern of the cosmic microwave background. Despite years of dedicated searching by instruments including the BICEP and Keck array telescopes, that signature has not been detected. Current measurements only place an upper limit on its possible strength, tightening the constraint with each new observation, but never quite finding the signal itself. If that signature is ever detected, it would provide remarkably direct evidence connecting today's structure to inflation's earliest moments. Until then, it remains one of cosmology's most anticipated, unresolved searches. Consider, for a moment, what the universe would look like if those initial fluctuations had never existed at all. A perfectly uniform early universe, with absolutely no density variation whatsoever, would leave gravity with nothing to work with. No region would ever pull ahead of any other. Matter would remain forever smoothly spread, with no mechanism to clump it into anything resembling a star, a galaxy, or an observer capable of studying the question. A universe without seeds simply never grows a garden. But there's another possibility worth examining honestly. What if the fluctuations had instead been substantially larger than what we actually measure? Regions of higher initial density would have collapsed more quickly and more dramatically, likely producing more extreme environments and a greater abundance of compact collapsed objects earlier in cosmic history. But here's an important correction to a claim you may have encountered before. Larger fluctuations would not have simply turned the entire universe into black holes. That's an oversimplification that doesn't survive contact with the actual physics. which depends on the precise amplitude, scale, and timing of any hypothetical increase, not some simple linear scaling toward total collapse. What we can say is this: the fluctuation strength we actually measure appears to sit within a range that permitted galaxies, stars, and stable chemistry to develop across cosmic time. Whether that range reflects deeper physical necessity, some form of statistical selection among many possible outcomes, or simply the conditions that happen to occur, remains a genuinely open question, and framing it as evidence of deliberate fine-tuning goes well beyond what the current evidence actually establishes. Here's the reveal this entire chapter has been building toward, and it reframes everything you've learned across this whole journey. The emptiness filling our universe, the staggering gaps between galaxies, the void spanning hundreds of millions of light years, the entire architecture of the cosmic web. None of it was imposed afterward, as some separate force acting on a previously uniform cosmos. It is the direct, traceable evolution of microscopic quantum uncertainty operating during the very first fraction of a second this universe existed, stretched to cosmic scale, then amplified by billions of years of gravity, working exactly as physics predicts. But here's what still remains entirely unanswered, and it's the deepest unresolved question this entire investigation has uncovered. We don't know what triggered inflation to begin. We don't know what set its duration, or what specific physics caused it to end when it did. And we don't know how to connect this entire framework to quantum gravity, the still unbuilt theory that would describe how gravity itself behaves at the smallest possible scales, the scales where our current physics simply stops providing reliable answers, which leaves us facing an unsettling possibility we haven't yet confronted directly. If inflation reshaped everything we can currently observe, what, if anything, existed before it? And does that question even have an answer science can ever reach? We may never know what came before, but we know, in extraordinary detail, what came after. And what came after is, when you sit with it honestly, one of the strangest outcomes physics has ever produced. Because nothing about the early universe guaranteed that any of this would happen. We already traced how those faint primordial fluctuations, stretched across cosmic distances by inflation, planted slightly denser and slightly emptier regions across an otherwise nearly uniform universe. What happens next is where dark matter, the invisible scaffolding we encountered earlier in this journey, finally does its slow, patient work. Dark matter halos, those gravitationally bound clumps of invisible mass, began forming first, collapsing under their own gravity long before ordinary matter could organize itself the same way. Hydrogen and helium gas, the only elements that existed in any meaningful quantity at this stage, began falling into those halos, drawn inward by gravity the way water collects in the lowest point of an uneven landscape. Inside those gravitational wells, the gas needed to do something specific before it could ever form a star. It needed to cool. Here's why cooling matters so much. Hot gas resists collapse, the same way steam resists condensing into liquid water until it loses enough heat. As hydrogen gas inside these early halos radiated away its thermal energy, it cooled, contracted, and fragmented into smaller, denser clumps, churned by turbulence the way cream folds and separates when stirred into coffee. Within the densest of those fragments, gravity finally won outright, compressing material until nuclear fusion ignited at the core. The first stars were born. Astrophysicists call this hypothetical first-generation population 3 stars, theorized to be composed almost entirely of hydrogen and helium, completely free of the heavier elements, called metals in astronomical terms, that pollute every star that has formed since. No confirmed direct detection of an actual population 3 star exists yet. Their predicted properties, extreme mass, blistering temperature, and unusually short lifespans make them exceptionally difficult to observe directly, and they remain, for now, a strongly motivated theoretical population rather than a confirmed observational fact. But here's where the story takes its first crucial turn. When these massive first-generation stars reach the ends of their brief lives, many almost certainly exploded as supernovae, scattering newly forged elements, carbon, oxygen, silicon, iron, and others, heavier still, into the surrounding gas. Picture a single match dropped into a perfectly clean glass of water, slowly tinting the whole glass with color. That's roughly the process. Each exploding star seeded its surroundings with the raw materials necessary for everything that followed. Those scattered metals settled into the next generation of forming stars, then the generation after that, with each cycle of stellar birth, death, and explosion, compounding the chemical complexity available to whatever form next. This is, quite literally, the origin story of every rocky planet, every molecule capable of complex chemistry, and eventually every biological possibility this universe has ever produced. Without those first violent stellar deaths, none of this would exist. Without them, there would be nothing but hydrogen and helium, forever. But forming the first stars was only the opening move. Building an actual galaxy, something stable enough to last billions of years, turned out to require winning a far more delicate ongoing competition. Galaxies grow through several different channels simultaneously. Smooth, gradual accretion of surrounding gas, the capture and absorption of smaller satellite galaxies, outright mergers between comparably sized systems, and slower internal reorganization that astronomers call secular evolution, the gradual reshuffling of stars and gas within an already formed galaxy over enormous stretches of time. Each of these processes is constantly pulling the galaxy in a different direction, growing it, reshaping it, sometimes nearly tearing it apart. And here's the genuine tension underneath all of this growth. Too much energetic violence from the wrong source can destroy a forming galaxy as easily as it can build one. When supernovae detonate inside a small, low-mass galaxy, the explosive energy can actually overpower the galaxy's relatively weak gravity entirely, expelling vast amounts of gas straight out of the system before it ever gets the chance to form additional stars. Picture trying to fill a paper cup with water from a fire hose. The shallow gravitational well of a small dwarf galaxy simply cannot hold onto material against that kind of explosive force. This single mechanism, called supernova feedback, is one of the primary reasons dwarf galaxies remain so persistently small and gas-poor throughout cosmic history. Larger galaxies face a different threat entirely. At the center of most massive galaxies sits a supermassive black hole, and when that black hole actively consumes surrounding material, it becomes what astronomers call an active galactic nucleus, radiating tremendous energy outward and heating the surrounding gas so severely that the gas can no longer cool and collapse into new stars. This process can effectively throttle a massive galaxy's own growth from the inside, a kind of internal regulatory mechanism preventing runaway expansion. So galaxy formation, at its core, is a constant ongoing negotiation between gravity pulling matter inward, cooling, allowing that matter to condense, turbulence churning and complicating the process, and radiation along with energetic feedback pushing back outward, sometimes gently, sometimes catastrophically. Every galaxy you have ever seen survived that negotiation. Most potential galaxies, almost certainly, did not. Here's the thing, most people don't realize about a galaxy's visible structure. Even something as iconic as a spiral galaxy's elegant arms remains, in certain important respects, scientifically unresolved. Astronomers have proposed multiple explanations for why spiral patterns form and persist, including density wave theories, in which the spiral pattern represents a slow-moving wave of compression rotating somewhat independently of the stars passing through it, the way a traffic jam holds its shape on a highway, even as individual cars continually enter and exit the slowdown. Other models point to gravitational instabilities and recurring, transient spiral patterns that form, dissolve, and reform repeatedly, rather than persisting as one single permanent structure. No single theory has been established as the complete universal explanation. Different galaxies, and quite possibly different processes operating simultaneously within the same galaxy, may require different combinations of these mechanisms. Underneath all of this visible structure, dark matter halos continue doing their foundational work, stabilizing each galaxy's overall rotation, while ordinary matter, the baryons forming stars and gas, reshapes the dark matter's central distribution through the same feedback processes we just discussed. This interaction creates genuine, measurable tensions that researchers actively use to test our models. The cusp core problem describes a persistent mismatch between how steeply dark matter should theoretically concentrate at a galaxy's very center, according to simulations, compared to what astronomers actually measure in real dwarf galaxies. The missing satellite problem describes a related puzzle. Standard simulations predict considerably more small satellite galaxies orbiting larger ones than astronomers have actually been able to detect. These remain genuine open areas of active research, not settled scientific facts. Environmental conditions ultimately determine what kind of galaxy results from this entire competition. Spirals, ellipticals, dwarf galaxies, galaxies that have stopped forming new stars entirely, called quenched galaxies, and irregular disorganized systems all emerge from the same basic underlying physics, shaped differently by their specific local environment, merger history, and feedback intensity. And then, starting in 2022, an instrument arrived that pushed this entire story to its breaking point. The James Webb Space Telescope, observing an infrared wavelength specifically suited to detecting extremely distant redshifted light, began spectroscopically confirming galaxies from a period of cosmic history no previous instrument could reach. In 2024, the JADES collaboration confirmed a galaxy called JADES GSZ 140, dating to merely 300 million years after the universe began. That galaxy's light has been stretched by a factor of roughly 15 during its journey to us, an almost unimaginable degree of cosmic redshift, pushing what was originally ultraviolet light all the way into the infrared range only Webb can detect. 300 million years sounds abstract until you compare it to the universe's full age of 13.8 billion years. That galaxy formed when the cosmos had completed only about 2% of its current lifespan, the equivalent of catching a fully developed adult within the first few weeks of an entire average human lifetime. Here's where it gets genuinely disturbing. That galaxy wasn't supposed to be there yet, at least not looking the way it does. Researchers expected early galaxies at this cosmic age to be small, faint, and barely formed. Instead, JADES GSZ 140 turned out unexpectedly bright, unexpectedly large, and unexpectedly metal-enriched, meaning it had already cycled through enough generations of star formation and supernova explosions to seed itself with heavier elements, all within a window of cosmic time that existing formation simulations struggled to accommodate. It wasn't alone. JWST identified an entire population of similarly luminous, unexpectedly abundant early galaxies, leading some researchers to describe a genuine tension with standard cosmological models, suggesting these galaxies were converting available raw gas into stars with implausible efficiency. But here's where honesty about the current state of the science matters enormously, because the picture has shifted as more detailed data accumulated. Some of the most extreme early, impossible galaxy claims have genuinely softened. Follow-up spectroscopic observations have revised both mass and distance estimates downward for several candidates, and researchers identified active galactic nuclei contributing unexpected brightness in cases that initially looked like pure stellar light, meaning some of that early luminosity came from actively feeding black holes rather than star formation alone. This doesn't erase the puzzle entirely, but it has measurably reduced its most extreme original form. What remains unresolved, and this is a genuine, ongoing scientific debate rather than a settled conclusion, is how rapidly stars, heavy elements, and central black holes assembled inside these earliest confirmed galaxies. Current cosmological simulations can reproduce many of the observed galaxy populations, but typically only by incorporating increasingly complex feedback prescriptions, detailed mathematical adjustments, calibrated to match observations rather than derived purely from first principles physics. That's not necessarily a flaw. It's simply an honest acknowledgement that our simulations currently require careful tuning to match what Webb keeps finding. So the open question remains genuinely open. Do these remaining discrepancies reflect gaps in our astrophysical modelling of star formation and feedback, observational selection effects favouring the detection of unusually bright outliers, or possibly something deeper, involving physics within the dark sector itself that current models haven't yet incorporated? Scientists actively studying this question do not agree on the answer, and presenting false certainty here would betray exactly what makes this such a genuinely live area of research. Step back from the cutting edge of current research for a moment, because a clearer pattern emerges from everything we've covered. Galaxy mass appears to be constrained from both directions simultaneously. Below a certain mass threshold, supernova feedback efficiently expels gas before substantial star formation can occur, the fire hose into a paper cup problem we already described. Above a certain threshold, gas heating from active galactic nuclei, combined with increasing scarcity of fresh, cool material available for collapse, throttles further growth from the opposite direction. Galaxies, in other words, exist within a genuinely narrow surviving range between two different ways of failing to form at all. And the broader cosmic context we traced earlier compounds this challenge over time. As cosmic acceleration continues separating unbound structures, the fresh material supply available to any given galaxy or galaxy cluster will eventually halt entirely as the surrounding intergalactic medium recedes beyond reach. The window during which a galaxy can actively grow, accumulate fresh gas, and form new stars is not permanent. It is a temporary opportunity, open for a finite stretch of cosmic time, closing gradually as the universe's accelerating emptiness eventually isolates. Every surviving structure, this entire chain, from primordial quantum fluctuations through dark matter halos, through the first fragile stars, through generations of stellar death-seeding heavier elements, through the genuinely difficult, competitive process of building a stable galaxy, raises an uncomfortable question worth confronting directly. Some thinkers have framed this remarkable sequence through what's called the anthropic principle, the observation that any universe capable of being studied by an intelligent observer must necessarily possess physical conditions compatible with that observer's existence. It's worth being precise about what this principle actually claims and doesn't claim. It describes a selection effect, a statement about which kinds of universes would ever contain someone positioned to ask the question in the first place. It is not, on its own, a mechanism that explains why the physical constants governing our universe took the specific values they did. Consider, for a moment, what a universe lacking dark matter's gravitational scaffolding might have looked like, or one where the primordial fluctuations had been essentially zero, smooth and featureless forever, or one where stable, long-lived stars capable of sustaining billions of years of steady fusion simply weren't possible under different physical constants. Any of these alternate conditions could plausibly have produced a universe with no galaxies, no heavy elements, no stable chemistry complex enough to support anything resembling biology, and consequently, no observer ever positioned to notice the absence. We exist at the end of an extraordinarily long contingent chain: primordial perturbations, gravitational collapse, the first unstable generation of metal-free stars, supernova enrichment, subsequent stellar generations, rocky planets, complex chemistry, and eventually, against significant odds at every single stage, something capable of biological complexity and, eventually, intelligence. But here's an important caution worth stating honestly before this goes any further. We should resist overstating Earth-specific conditions, our particular chemistry, our particular planetary environment, as proven universal requirements for any possible form of life anywhere in the cosmos. Whether some form of deeper physical necessity required these specific outcomes, whether a multiverse of varied physical constants makes our particular combination simply one viable outcome among countless failed alternatives, or whether some other explanation entirely accounts for why any of this worked, remains a genuinely unresolved question sitting at the boundary between physics and philosophy. No camp has settled this argument, and presenting one interpretation as established fact would misrepresent where the actual evidence currently stands. What we can say with confidence is this: galaxies are not the universe's default outcome. They are temporary hard-won islands, assembled against a competition between gravity and destruction that could have gone differently at nearly every step, built from the wreckage of dying first-generation stars, sustained by a narrow surviving range of mass, and granted only a limited window of cosmic time before accelerating emptiness eventually isolates them entirely. And within at least one of those temporary islands, something even stranger happened. Matter rare enough, complex enough, and improbable enough arranged itself into something capable of looking outward, tracing the entire chain back to its origin, and asking why so much of everything around it turned out to be empty. But understanding why galaxies exist against these odds only sharpens a far larger question we still haven't fully confronted, because everything we've traced, from inflation's first fluctuations to the last surviving galaxy drifting alone in an accelerating darkness, points toward a future state more total and more final than anything we've discussed so far. What happens after the very last star, anywhere, finally goes dark? Here's a fair warning before we go further. We're about to travel across timescales so enormous that the numbers themselves stop feeling like numbers. They become more like horizons, markers of how far human understanding can extend before the scale simply outpaces our ability to feel it. Hold on to something familiar, because we're going to need it. This decline isn't some distant future event. It's already happening right now, measurably, across the observable universe. Cosmic star formation peaked roughly 10 billion years ago and has been declining ever since, as galaxies gradually consume their available gas, heat it past the point where it can cool and collapse, eject it outward through the same feedback processes we traced in the previous chapter, or simply lose access to it as accelerating cosmic expansion separates them from the surrounding intergalactic reservoirs that once replenished them. Each of those four mechanisms chips away at the raw material the universe needs to keep building new stars. We currently live inside what astronomers call the stelliferous era, the age defined by ongoing star formation and starlight as the primary source of energy lighting up the cosmos. Here's something worth stating clearly before we go any further. Every timescale from this point forward represents a theoretical extrapolation built from our current best physics, not a precisely scheduled cosmic appointment. Treat these numbers as informed projections, almost certainly directionally correct, rather than fixed dates circled on some cosmic calendar. With that caveat firmly in place, here's what current models suggest. The stelliferous era will likely continue for an extraordinarily long time, sustained largely by red dwarf stars, the smallest, dimmest, and most miserly stars in the cosmos. Our own sun will exhaust its remaining core hydrogen in roughly 5 billion years. A typical red dwarf, by contrast, fuses hydrogen so slowly and so completely, using nearly all of its fuel, rather than the roughly 10% our sun will ever access, that models estimate lifespans stretching across trillions of years. Picture two campfires built from identical amounts of wood, one burning fast and bright, consuming everything within hours, the other smouldering so slowly it could theoretically still be glowing 1,000 years later. Current projections suggest the stelliferous era, sustained by these patient, miserly stars, may continue until the universe is roughly 100 trillion years old, something on the order of 7,000 times its current age. Even after the very last star finishes forming and burning, matter itself doesn't simply vanish. White dwarfs, the dense, slowly cooling remnants left behind by stars like our sun, will persist. Neutron stars, the even denser remnants of more massive stellar deaths, will persist alongside them. Brown dwarfs, objects too small to have ever sustained full hydrogen fusion in the first place, drift on essentially unchanged. Planets, stripped of their parent star's light and warmth, continue orbiting dark, frozen centers, and black holes, having consumed whatever fell within reach, remain as well, indifferent to the absence of starlight around them. Across spans of time even longer than the stelliferous era itself, gravitational interactions between these scattered remnants will continue reshuffling the cosmic furniture. Close encounters between drifting objects will occasionally fling one of them outward entirely, ejected from its host galaxy into the deepening dark between structures, while others will spiral gradually inward, eventually merging with the supermassive black holes anchoring galactic centers. It's a slow, patient process of cosmic sorting, scattering some remnants to the furthest reaches of intergalactic space, while consolidating others into ever more massive central giants. And in this distant future, models predict an object that has likely never existed yet anywhere in the universe. A black dwarf, the theoretical end state of a white dwarf that has cooled completely, radiating away its last residual heat until it goes fully dark, no longer emitting any detectable light at all. Forming one requires a cooling process, estimated to take well beyond the current age of the universe, meaning every white dwarf currently in existence remains, by definition, too young to have completed this transformation. But here's where the story takes a turn that should genuinely unsettle you, because not even black holes, the most consuming, most permanent-seeming objects in the universe, last forever. In 1974, physicist Stephen Hawking proposed that black holes are not perfectly black after all. Through a subtle quantum mechanical process occurring near a black hole's boundary, black holes should slowly radiate energy outward, gradually losing mass over time in a process now called Hawking radiation. This remains one of the most influential and widely accepted theoretical predictions in modern gravitational physics. And yet, despite its broad acceptance, it has never been directly detected for any actual astrophysical black hole. The predicted radiation from a black hole the mass of our Sun would be colder than the background temperature of the universe itself, making it, for all practical purposes, currently undetectable with any existing instrument. Here's the counterintuitive part. Smaller black holes radiate faster than larger ones, meaning the smallest black holes evaporate first, while the largest, most massive black holes survive for vastly longer stretches of time. A black hole with the mass of our Sun, according to Hawking's calculations, would require approximately 10 to the 67th power years to fully evaporate, a number so large that comparing it to the universe's current age of 13.8 billion years feels almost meaningless, the way comparing a single grain of sand to the entire visible universe still somehow undersells the actual gap. And buried inside this slow evaporation sits a genuine unresolved conflict that has occupied theoretical physicists for decades. Hawking's original calculations suggested that the radiation escaping a black hole would be purely thermal, meaning it would carry no information whatsoever about whatever matter originally fell inside. But quantum mechanics insists, as one of its most foundational principles, that information cannot simply be destroyed. If a black hole eventually evaporates completely, and the radiation it released never carried out information about what fell in, then where did that information go? This is the black hole information problem, a genuine, unresolved collision between general relativity and quantum theory that remains one of the most actively studied open questions in all of physics. No solution has achieved consensus. The puzzle remains exactly that, a puzzle. Here's a question worth confronting directly, because it threatens to upend the entire timeline we've just traced. Some grand unified theories, frameworks attempting to merge the fundamental forces of physics into a single unified description, predict that protons themselves, the basic building blocks of every atom in existence, might not be permanently stable. If true, individual protons would occasionally, exceedingly rarely decay into lighter particles entirely. No experiment has ever observed this happening. Not once. The Super Kamiokande detector in Japan, a massive underground facility built specifically to search for this exact signature, has watched patiently for decades, without recording a single confirmed event. That absence of detection has allowed scientists to place a lower bound on how long a proton's partial lifetime must be, currently exceeding roughly 10 to the 34th years, depending on the specific decay channel being tested. Think about what that number actually implies. If protons genuinely never decay at all, remaining permanently and absolutely stable, the universe's distant material future looks radically different from a future where they eventually do. Stable protons mean ordinary matter, however diffuse and however isolated, persists indefinitely. Unstable protons mean even the most basic building blocks of existence are, on long enough timescales, temporary. Current experimental evidence cannot resolve which of these is actually true. It can only continue pushing the lower limit higher with each passing year of careful, patient, fruitless searching. Here's where all of these threads converge into a single overarching concept, and it's worth being precise about what it actually means, because the popular version of this idea gets mangled constantly. Physicists describe the universe's likely ultimate fate as heat death, though that name itself slightly misleads. Heat death does not mean energy disappears from existence. Energy, according to one of physics's most fundamental laws, cannot simply vanish. What heat death actually describes is the exhaustion of usable energy, specifically the gradients, the differences in temperature, density, or organization that allow any process whatsoever to do work. Here's an analogy that captures the underlying logic. A waterfall can turn a turbine and generate electricity precisely because water sits higher on one side than the other, creating a gradient the system can exploit. Once all the water has settled into one perfectly level pool, the water hasn't disappeared. It simply can no longer do anything because the height difference that made work possible has vanished entirely. Heat death describes the universe reaching that same state of thermal equilibrium, where every meaningful gradient has finally smoothed out and nothing remains capable of doing work, regardless of how much raw energy technically still exists. And here's the role acceleration plays in sealing that fate. As cosmic expansion continues separating unbound structures across ever-increasing distances, the remaining particles, radiation, stellar remnants, and dark matter scattered throughout the cosmos will become increasingly isolated from one another, diluted across an ever-expanding volume, until even the faint, scattered energy gradients that currently still exist eventually smooth away entirely. But here's where intellectual honesty matters most, because the universe's actual ultimate fate remains a genuinely unresolved scientific question, not a settled conclusion. If dark energy behaves precisely the way the simplest cosmological constant model predicts, accelerating expansion continues indefinitely, isolating structures and gradually approaching the heat death scenario we just described. But if dark energy instead behaves like a more extreme phantom energy, with properties that grow stronger rather than remaining constant over time, the resulting scenario, called a big rip, would tear apart galaxies, solar systems, and eventually even atoms themselves, as expansion accelerates so violently that no force, however strong, could hold any structure together at any scale. A separate, far more speculative possibility involves vacuum decay, the theoretical possibility that the universe's underlying vacuum state, the lowest possible energy configuration of empty space itself, might not be perfectly stable, and could potentially transition to an even lower energy state somewhere, at some unknown moment, triggering a catastrophic transformation that would expand outward at the speed of light. Both the probability and the timescale of this scenario remain almost entirely unknown, and it should be treated as exactly what it is, a theoretically possible but highly speculative scenario, not an established prediction. And here's a genuine complication worth returning to directly, connecting back to evidence we already encountered earlier in this journey. The DESI collaboration's recent measurements, hinting that dark energy's strength might evolve over cosmic time rather than remaining perfectly constant, could meaningfully modify any of these projected endings. Evolving dark energy could potentially postpone heat death, alter its specific character, or, under certain theoretical scenarios, even eventually reverse accelerating expansion entirely, current evidence simply cannot determine with certainty which of these long-term outcomes our actual universe is heading toward. Scientists studying this question do not agree, and that disagreement is itself an honest reflection of how much remains genuinely unknown. Step back from these individual scenarios for a moment and look at the larger shape of time itself. The eras of active structure, star formation, galaxy growth, the entire luminous universe we've spent this whole journey exploring, occupy what amounts to an almost vanishingly brief opening chapter compared to the unimaginably longer future stretch of dilution, isolation, and eventual equilibrium that likely follows. We are not living in the universe's middle act. We are living, almost certainly, somewhere very near its beginning, during the brief window when usable energy gradients still exist in abundance, when stars still ignite, when light still travels freely between galaxies still close enough to see each other. We've covered an extraordinary distance together across this entire investigation, from a sky that looked deceptively full, to deep fields revealing thousands of hidden galaxies, to invisible scaffolding holding entire clusters together, to an acceleration nobody expected, to voids larger than anything intuition prepares you for, to horizons quietly closing around our own ability to witness the cosmos, to the quantum origins of every structure that has ever existed, to galaxies surviving against genuinely difficult odds. That is a lot to carry. Take a slow breath, right where you are. You've earned it. Let's bring every piece of this back together, because each discovery we've traced connects directly into the next. Emptiness, we now understand, did not appear from nothing fully formed. It emerged from expansion acting on tiny primordial density differences, the faint 1 part in 100,000 fluctuations imprinted during inflation's earliest fractions of a second. Dark matter concentrated rare ordinary matter into the scaffolding capable of forming galaxies at all, while dark energy increasingly isolates everything not already gravitationally bound together, carrying unbound structures beyond any future hope of contact. The cosmic web's voids and filaments, the closing horizons we traced, the brief, contingent chain of stellar generations required to build anything resembling chemistry or biology, all of it traces back to that same originating mechanism, expansion, magnifying microscopic imperfection across billions of years. Here's something worth stating with complete clarity before we close. Emptiness enabled stable galaxies to form and persist. It did not prove that the universe was somehow designed for the purpose of producing observers. Those are two very different claims, and only the first one survives careful scientific scrutiny. And yet, somewhere inside that almost incomprehensibly vast emptiness, on a small rocky planet orbiting an unremarkable star, something remarkable happened anyway. Matter arranged itself into a configuration rare enough, complex enough, and improbable enough to become aware of its own surroundings, capable of tracing the entire chain backward, from inflation's quantum fluctuations, through galaxy formation, through stellar nucleosynthesis, all the way to this very moment, sitting with this realization. Our understanding cannot stop entropy from increasing. It cannot halt cosmic expansion, prevent the slow death of every star, or reverse the gradual isolation awaiting every bound structure in the universe. We have not solved the universe's fate. We have simply, carefully, earned the right to describe it honestly. The universe is empty because structure is temporary, because separation dominates over connection at the largest scales, and because expansion, once begun, appears to endure far longer than anything it ever assembled. That is not a comforting conclusion, but it is, as far as the evidence currently allows us to say, a true one. And within that immense accelerating darkness, for one brief improbable moment, on one small world circling one ordinary star, rare matter became aware enough to look outward, to measure the silence between the galaxies, and to finally understand exactly what that silence actually means. Go back for a moment to that night sky we started with. The one that looks so full, so close, so generous with light. You know what was actually written across that darkness now. Galaxies hiding in directions that looked empty. Voids wider than the mind can comfortably hold. Distances that keep growing, even as you sit here listening to this. A universe spending almost all of itself on the space between things, rather than the things themselves. And somewhere inside that emptiness, on this particular night, in this particular room, a small arrangement of matter became complex enough to ask why. That arrangement is you. Not small, because the universe is large. Rare, because the universe is empty. Almost everything stayed dark, stayed scattered, stayed silent. You didn't. That's not a comforting thought, not exactly, but it might be the closest thing to one this universe actually has to offer. Thank you for staying with this all the way to the end. If tonight changed even slightly how you see that sky, a like and a subscribe lets me know. There's more darkness out there still waiting to be understood, and I'd like to keep walking through it with you. Sleep well. The sky will look different tomorrow. Good night.